Good morning, everyone. Today we will continue the discussion of mutual inductance, and we will talk about how energy, how much energy, or how do we determine what energy is stored in a mutual inductance configuration. So to remind you, we know that the energy stored in a self-inductance, so we have I of t and V of t. So you established in the last semester in networks 1 that the energy stored in the inductor is half L I squared. And we will kind of rederive this right now when we are as we are working on energy for the mutual inductance. So we will rederive this. But remember this formula. The question is, if I have a situation where I have some sort of mutual inductance, what would the energy be in the self-inductances and the mutual inductance? How can we calculate it? Right, so let's and to calculate it we will do a thought experiment. But before we do the thought experiment, we need to set it up. So I'm going to set it up as a mutual inductance. Right, so I have a mutual inductance, I have L1, L2, and then I have M. And then I have, I'll follow the convention that the current is flowing into the dots. Right, so I have I1 of t, I have I2 of t, and then I have V1 of t, V2 of t. Right? So the assumption here is that I have control over the primary and the secondary circuits. I can control the current to be anything I want. So the experiment goes as follows. I'm gonna set the experiment up such that I1 of t starts at 0 and goes from 0 all the way to a peak of I1 and then stays at I1. So this is I1. And it reaches I1 at T1. Right? In the meantime, I2 of t remains 0. So from t equals 0 to t equals T1, I2 of t, remains 0. Right? Then what will happen is that from T1 to T2, nothing will happen for as far as I1 is concerned. It will remain constant. We're setting up the experiment such that it remains constant, while I2 is going to grow from 0. I2 is going to grow from 0 all the way to I2 capital, to this constant. Right? And it's going to remain there. So the question is, what would the energy stored in the mutual inductance configuration be in that scenario? We know that the initial energy will be 0, right? Because initially there is no current anywhere. The currents everywhere are 0. I1 and I2 are 0. So intuitively there is no energy. We push in the currents, and that brings in energy into the system. Question is, how much energy? How do we quantify it? Okay. So let's start with the time period 0 to T1. What's happening in that time period? Well, I2 is 0, so there is definitely no energy being extracted. Right? Let's think about it this way. Any amount of energy that ends up being built up inside this configuration, right, has to come from somewhere else, right? Any amount of energy that ends up being stored in here has to come from outside of this configuration. Energy cannot be created out of nothing. Energy can only be moved around, right? So any energy that ends up being stored in here has to come from outside, has to come from any circuitry outside. We could have sources outside, whatever, testing apparatus that kind of pours in energy into the setup, right? So when T is 0 to T1, no energy can come from this part of the circuit, from the secondary side, because what? I2 is 0, right? So because I2 is 0, no energy can come from this side. right? All the energy is coming from this side. All the energy pumped into this configuration is coming from this side. Well, what's that energy? Well, we know the power, right? The power, P of t coming in, is just V1 of t, I1 of t, right? That's what the power is. And we know that for, in this case, V1 is going to relate to I1 using the self-inductance formula, right? There is no mutual component because I2 is 0. So it's going to be L1 di1t over dt I1 of t. Right? So the energy E1, the energy that gets accumulated into the configuration for t from 0 to t1 is just the integral from 0 to t1 of p of t d of t. And we just have to do the calculus. We just have to go through the calculus to calculate this. Right? So this is going to be 0 to t1 L1 di1 over dt dt. Right? I can, I mean, although a mathematician will have a stroke if I do this, I mean, this is essentially, I'm doing manipulation of the differentials to do the integration. Right? And there's I1t, of course. Right? So I'm just doing exchange of variables essentially, right? So you can take L1 out, 0 to T1, I1 of t, di 1 of t, right? And I know how to integrate this. So this is L1, I1 of t squared over 2 from 0 to T1, right? And this is going to be half L1. What's I at T0 is going to be 0. I at T1 is just I1 capital, right? So this is going to be I1. I called it I1, right? I1 capital squared, right? So this would be the energy that gets stored into the configuration as I slowly increase I1 from 0 to I1 t from 0 to I1 capital. Okay. Now I want to investigate what happens when t is larger than t1, less than t2. Now I'm ramping up I2 from 0 to I2, right? What are the voltages in this case? So recall, in this case we have both I1 and I2. So in this case we will have V1. So recall, V1 is going to be the self-inductance L1 di1 by dt. And then I have the mutual inductance, M di2 by dt, and then V2 is going to be M di1 by dt, L2 di2 by dt. And let's examine the circuit to determine the signs. Right, so for the mutual inductance for V1, I2 is going into the dot, and the polarity of V1 matches the dot, so this will be positive. For the mutual voltage in V2 and L2, well, I1 is going into the dot, and the dot here matches the polarity of V2. So this also will be positive. Right? This also will be positive. Right? Now, remember in our experiment, I1 goes from 0 and then remains constant. Right? So this is T1, and then I2 at T1 is 0, and then it starts growing until it hits I2 and it hits I1. So the key thing here is that in period 2 of our experiment, there is an I1, but this I1 is constant, is fixed. So that means I can take this out. So this becomes 0. Right? By design, I1 is constant. Right? So V2 will solely be due to equal to this. Right? So now what is the energy during this period number 2 from t equals T1 to T equals T2? How much energy is going to be drawn from this part of the circuit now? You know, this part of the circuit. Right? So again, this is a problem of self-inductance because V2 has only this component. So we do the integration. E2 is going to be just the integral from T1 to T2 of P of t dt. P of t in this case is just going to be, remember, E2 is just the energy coming in from coil 2, from the circuit connected to coil 2. So that's going to be V2 of t, I2 of t, dt. This equals integral from T1 to T2. V2 of t is just L2 di2 dt, I2 dt. I can do this integral L2. So this is I2 di2. This is just I2 squared t over 2 from T1 to T2. And I know that at T1, I2 is 0. At T2, I2 is I2 capital. So I end up with the energy coming in from the secondary, from the circuit connected to the secondary coil is half L2 I2 squared. Okay. So now we found out that during T from 0 to T1, I have E1 energy coming from coil 1, which is half L1 I1 squared. And then during T from T1 to T2, I have E2 energy coming from coil 2, from the circuit connected to coil 2, equal to half L2 I2 squared. But I'm not done yet. Why am I not done? Well, during the period that energy is coming in from circuit 2 connected to coil 2, there is also extra energy coming in from circuit 1 connected to coil 1. Why? Because during this period there's still V and I going through into coil 1, right? So although I1 is not changing, let me go back to this equation. So there's something else I can see here. Although I1 is not changing, this is 0, right? So this is also 0. I1 is not changing this period during this period. I still have this term here that's a function of I2 that changes V1. And V1, even though I1 is constant, when V1 changes, that changes the amount of power going into the system. So you have extra energy during period 2. You don't only have energy coming from circuit 2, you have also energy coming into the configuration from circuit 1. What is that energy? Let's call that E2 prime. So this is the energy coming in period 2 that's coming in from coil 1. That's going to be the integral of T1 to T2. The power coming from coil 1. What's the power coming from coil 1? It's V1 of t, I1 of t, right? dt. And we said during test period number 2, or experiment, during the period number 2 of our test, of our thought experiment, this is what V1 is. Because I1 remains constant, so V1 is this m di2 by dt. So V1 is going to be m di2 by dt, and then I have I1t dt. dt goes with dt, I end up with m, right? Notice here I'm integrating with respect to I2. That means what? I1 is constant, right, with respect to I2. I1 is actually, during this period, I1 is just I1. It's constant, it does not change. So I can also take it out. And I end up just integrating di2, which is just I2. So which is I2 at t. So this is m I1, I2t integrated between t1 and t2. I2t at t1 is 0, I2t at t2 is I2. So energy in period 2 coming from coil 1 is going to be m I1, I2. Right? So finally we discovered that the total energy, after we go through all the steps, the total energy that gets stored into the configuration is the sum of all the energies, which is going to be half L1 I1 squared plus half L2 I2 squared, kind of what we expect, right? But then we will have plus m I1 I2. This is the total energy. Remember, see, it has an extra term here that has to do with the mutual inductance, which is also, it also has a quadratic term, right? It has a multiplication of two currents, but now the two currents are the two separate coil currents. So it has an interesting form, right? But this would be the energy, right? And we can write it. Although we did the thought experiment where the currents became constant at the end, we could imagine that the currents could be those constant currents could be any current, really, right? Doesn't matter. They could be any current. The current could change at will, and it will still give us the correct formula for the energy. So the most general formula for energy is going to look like this. The energy at any point in time is just half L1 I1 of t squared plus half L2 I2 of t squared plus m I1 of t I2 of t. Right? Now, this is the case if we have this configuration. We have the two dots like this, and I have I1 going into the dots, and then V. Right? What happens if I have a configuration where the dots are reversed like this? Right? I1 is still going in, and I2 is still going in, and V1 and V2 is still like that, right? But the dots are inverted. You could do the derivation, but I won't redo it. It's the same thing. It's just repetition of the same thing with changing signs. What turns out to the energy turns out in this case to be half L1 I1 squared plus half L2 I2 squared minus m I1t I2t. The energy is subtracted. Energy is less than what you expect from two inductors rather than more. Right? I won't do this. You can easily redo the steps that we did and you will get that result. Right? But that notice that the energy stored in the mutual inductance configuration is going to depend on the orientation of the dots. All right. So this is the energy, right? And it could be positive or negative. So let me rewrite it actually to express that. So E at any point in t is half L1 I1 squared t plus half L2 I2 t plus minus m I1 t I2 t. This plus minus signifies that the energy could be slightly larger than the energy due to the two currents with the self-inductances due to mutual inductance. That is if the dots align, and it could be slightly less or somewhat less if the dots don't align. Now, there's something more we can say about this. A coupled system is essentially a two-port network, right? So it is essentially a passive network. What does a passive network mean? It means that it's not a circuit that can generate energy. There's no generator in there. Energy has always to come from outside. Energy has either to come in from here or here, right? And whatever energy stored inside can go out. But you cannot get, at any point in time, you cannot get E less than 0. What does E less than 0 mean? It means that this box here generated energy and provided energy beyond itself, right? So typically a generator would give you like a generator, something like a source that generates energy, right? The energy that it absorbs is less than 0, right? It's negative because it's not absorbing energy, it's generating energy. This being a passive circuit and not a generator, it cannot generate energy. At any moment in time, E of t has to be larger than 0. Okay, so what can this tell us? We can use this fact to tell us something about the relationship between L1, L2, and M. But we have to do a bit of algebra first. So let me rewrite the energy equation here. So E equals half L1 I1t, and I'm going to suppress the t. It's known that I is a function of t. So we don't need to keep writing it down. So plus half L2 I2 squared plus minus M I1 I2. Now I'm going to add some stuff here. I'm going to add plus half M squared over L2 I1 squared minus half M squared over L2 I1 squared. I did not change a thing, right? This is positive, negative, the same number, 0, right? So this minus this is 0. So I did not really change the expression, but this now allows me to kind of like couple terms together and collect terms together. So I can couple this with this, and I can couple this with this, right? And what happens when I do that? Well, let's see. We end up with E. Let me first couple this with this. I end up sorry, I made a mistake. What I meant with the coupling is I want to couple this with this, and then I want to collect those terms together, right? So what happens when I couple this term with this term? Let me take the half out. I end up with half L1 minus M squared over L. This is not L squared, this is L2 over L2 I1 squared. I took the half and I1 out, and then I have this term. Now in this term, let me take half L2 out. So this is going to become plus half L2. So let me multiply this by L2, divide by L2. It's still 1, it's the same. So I took out half L2, and then multiply this by 2 over 2. So this is 2L2 over 2L2. So I take half L2 out, I end up with I2 squared. I took now half L2, I end up with plus 2M over L2 I1 I2, right? And I took again, I have L2 over L2 here, so I took half L2 out. I end up with plus M squared over L2 squared. I end up with this expression, I1 squared, of course. Right. Now this is a perfect square, right? I can rewrite this. So let me write this as half L1 minus M squared over L2 I1 squared plus half L2. Oh, remember there's a there's a plus minus here, right? So this is plus minus, right? But this is a perfect square. This is something squared plus another thing squared. What's the first thing squared? It's I2, right? What's the second thing squared? It's M over L2 I1. So there's M over L2 I1, right? So this is a perfect square. So I take I2 squared, M squared, I1 squared over L2 squared, right? And then 2 times the first and the second, but I have positive negative here, so I have positive negative here, right? So this is the energy expression. Notice what happened here. We said energy needs always to be larger than 0, right? Well, this term is squared. So regardless of what happens inside here, this term will always going to be positive, right? This term is not squared. So this expression needs to always be larger than 0. So L1 minus M squared over L2 has to always be larger than or equal to 0. Let's rearrange rearrange terms in this inequality. So I end up with M squared over L2 less than or equal L1, M squared less than or equal L1, L2. So M has to be less than or equal square root of L1, L2. Right? So this energy calculation gives us an upper bound on M. M can never be higher than the geometric mean. So this kind of thing where you take L1 times L2, when you multiply two numbers together, you take the square root, is called the geometric mean. Right? M has an upper bound, which is the geometric mean of L1 and L2. This allows us to introduce a new constant called the coefficient of coupling, which is just defined as k equals m over square root L1, L2, right? Or another way of writing it is that m equals k square root L1, L2, right? Because m can never be higher than square root L1, L2, that means that k is always going to be larger than or equal 1, less than or equal, larger than or equal 0, less than or equal 1. So the coefficient of coupling is always going to be from 0 to 1. It is a measure of, right, another way also of writing this, right, since k is from 0 to 1, that means that m is larger than 0, less than square root L1 and 2. So all those statements are equivalent. So k is a factor from 0 to 1 that is a measure of how tightly the coils are coupled with each other. Maximum coupling, meaning the flux in coil 1 appears fully in coil 2, or the flux in coil 2 appears fully in coil 1, means a coefficient of 1. If the coupling is weak, the coefficient will be closer to 0. Right? So typically, tightly coupled cores will have a k that's larger than or equal to 0.5, typically. Weakly coupled cores will have k that's less than or equal to 0.5. Let me do this. Larger than 0.5 and less than or equal to 0.5. Right, so it's a measure of how strongly the coils are coupled with each other. Right? If the two coils are far apart from each other, then k tends to be very close to 0. Okay, so that's coupling. So we know how to analyze circuits with mutual inductance, we solved a lot of circuits, examples on that. We know how energy factors in, and we introduced the concept of coefficient of coupling from an energy consideration argument. All right. Let me do an example. So you're given this configuration. So you're given, it's an AC circuit. So you have, I'll have my phasor, 24 volts, 0 degrees, and it goes into this resistor. It goes into a coil, inductor, the impedance of J 1 ohm, right? And then I have another inductor, J 4 ohm, and then I have 4 ohm, right? And then I have J 2 ohms as the coupling impedance, the mutual impedance. This is the mutual impedance, right? That's not that's not the only information I'm giving you. I'm telling you the coupling coefficient is 1, meaning those two coils are very tightly coupled. The question is, what is E, the energy stored in the coupling configuration, coupled coils at t equals 5 milliseconds. Right? Oh, and the other thing I'm giving you is that L1 equals 2.653 millihenry, L2 equals 10.61 millihenry. Right? So we want to solve this problem. Okay? So first step is that I know that the coupling coefficient is 1, right? That means that what did we say? K equals m over square root L1, L2. If k equals 1, that means that m equals square root L1, L2. Right? So we know what is 2.653 times 10.61, and then millihenry squared square root. Okay, so that's going to be, if we do the math, that's going to be arithmetic, that's going to be 5.31 millihenries. Okay, that's fine. Now we want to calculate the energy. To calculate the energy, we need to know the currents. So let's do mesh analysis here to find the currents. Or furthermore, to do energy, we don't need the currents. We don't only need the currents in the phasor domain. We have to translate them later after we find the values as phasors. We need to translate those phasors into the time domain. So we want to go back to the time domain so that we can get the exact instantaneous value of the current to calculate energy. But let's first solve for I1 and I2 in the frequency domain, in the AC, using AC analysis, phasor analysis. Nothing new here, we did that already. So let me look at the circuit, let me look at mesh 1, let me do the mesh 1 KVL equation. So that's going to be 24, right? And then I1 is going to be multiplied by the impedances in the loop, the self and the 2 ohm. So that's going to be 2 plus J. Right? But then there's a mutual term that depends on I2. So that mutual term is J2 times I2. J2 times I2. Now the question of the sign. Well, oh, I forgot to give you the dots. That's very critical. The dots are like this. Okay. Okay, what about the sign? Well, I2 is leaving the dot, so that's negative. The KVL voltage is in the same orientation as the dot, so the sign doesn't change. So this becomes negative. And then equation 2 is 0, and then equation 2 is for loop 2. Let me do the I2 term, so that's going to be 4 plus J4. So that's 4 plus J4. That's the resistor, and the self term, I2, plus I have the mutual term, which is J2, I1. Now, what about the sign? Well, I1 is going into the dot, which means it's positive, right? But we're not done yet. I'm moving in this direction in the loop, right? I'm moving clockwise. So the KVL voltage, I'm plugging into the KVL equation, is going to have an opposite polarity compared to the dot. So this will be also negative, right? So I write that as a matrix equation. Oh, by the way, I think I got a question from one of you about whether linear algebra is a prerequisite for this course. Linear algebra is not a prerequisite for this course. What we're doing here with matrices and matrix multiplications and using Kramer's rule and doing matrix inversion, all of that, I mean, that's basic matrix manipulation. I believe you covered all of this in circuits 1, in networks 1. You must have covered Kramer's rule and how to write matrices of equations like that. So this is not full-blown linear algebra. Don't think this is linear algebra. This is just basic matrix manipulation where you just know how to write stuff in matrix format, do matrix inversion, and do Kramer's rule. And I'm fine with you, just doing it in MATLAB. You don't have even to know how to solve it on pen and paper, but you just need to have enough know-how to at least do it in MATLAB. Okay, so that's what I'm expecting here. I'm not expecting you to be proficient in linear algebra. That's just enough, and just to the extent to what you already learned in networks 1. Okay, so let me rewrite those equations as a matrix equation. So it's going to be minus 2j, and then minus 2j, and then 4 plus j4. And then I have I1, I2 equals 24, 0. Okay. And now I can plug this in MATLAB and do the inverse and whatnot, and I solve for I1 and I2. And this is what I get. I get 9.414 with an angle of minus 11.31 degrees and 3.328 with an angle of 33.69 degrees amps. Okay. Now we said we want to convert this to the time domain. To convert to the time domain, you need to know what frequency the AC system is operating at. So I'm going to assume, the assumption is that this is a typical AC network that you would find in any utility network, right? So this will be 60 hertz. So what would omega be? Omega would be 2 pi 60, which is approximately 377. Okay, so I could convert this to the time domain as 9.414 cosine omega, which is 377 t minus 11.31 degrees, and I2 of t equals 3.328 cosine 377 t minus 33.69 degrees. Now, this is typically written that way in the time domain, but remember always, as I said previously, this is an abuse of notation. Why? Because this term here is in degrees, but this term here is in radians. Omega times t is in radians. So you have to be careful here. You cannot just subtract the numbers and add the numbers directly. This is just notation, right? Before you can combine those angles, you have to make sure that they have the same units. Right? So please remember this. Okay. So I want to find the energy at t equals 5 milliseconds. At t equals 5 milliseconds, well, what's the angle here? It's 377. 5 times 10 to the power minus 3, that's equal to 1.885 radians. Again, before I merge this radians here with this degrees, I either have to convert this degrees into radians, or I have to convert this radians into degrees. So let me do this. How do I convert this? I multiply it by 180 and divide by pi. When I do this, I get 108 degrees. Plug that back in, I end up with I1 of t equals 9.414 cosine 108 degrees minus 11.31 degrees, and I2 of t equals 3.328 cosine 108 degrees plus 33.69 degrees. Right, I can do this whether in MATLAB or using a calculator. I end up with I1 of t. Well, I1, this is not t in general, this is I1 at 5 milliseconds. This is I2 at 5 milliseconds. Right, so I1 at 5 milliseconds is going to be minus 1.1 amp if I do this calculation, and I2 at 5 milliseconds is going to be minus 2.61 amps. Right? Energy now is just half L1, which is 2.653 millihenry, I1 squared, plus half L2, which is 10.61 millihenry, I2 squared, which is minus 2.61 squared, right? And now comes the mutual term. In this case, it's minus Mi1, I2. Why? Because the way the circuit is drawn, remember, I had the dots here, but I1 is going in and I2 is going out. So this is equivalent to the dots being reversed, right? Because I2, you can imagine that I2 is coming in this direction, inside here, right? So this is equivalent to the dots being inverted. So that's why this is going to be a minus sign. Minus 5.31 millihenry, that's the mutual inductance that we calculated. And then I1 minus 1.1, I2 minus 2.61. Crunch those numbers and we end up with the energy stored in the configuration being 22.53 millijoules. Right? That's the examples. Next, we will start talking about the ideal transformer, which is the last topic in this chapter. All right. So let's talk about the special case of the ideal transformer. Right. So this is the ideal transformer is an example of coupled circuit. So it's just coupling between two coils, right? But it is like an idealization, right? So although it's an ideal case, it's an important case. I mean, it's an important edge case to study. because most transformers that are practical transformers that are built and utilized by power distribution companies and utilities, most transformers are by design uh, uh, built to be as close to an ideal transformer as possible. It's desirable to have the characteristics of an ideal transformer, right? So what makes an ideal transformer? Well, you need to have some kind of magnetic core, magnetic material. Magnetic material is just material that amplifies the magnetic field, and you have two windings, right? So this is very good magnetic materials. How do you specifically remember your physics? You don't have to know those details, and I'm not sure how much physics you covered here, but you should know that there's something called permeability, roughly, for magnetic materials, and the higher the permeability, the more magnetic the material, right? So this is a measure of the magnetic property of materials of a material. The higher the number, the better this material at amplifying the magnetic field. So the idea is that you have two coils like that. Because this material amplifies the magnetic field, this material collects the flux and guides it towards the other coil, right? So this bunches the flux together and steers it towards the other coil, so the two coils get incredibly coupled. This allows you to get K as close as possible to 1, right? So K gets very close to 1. Right? So this is the idea. This is the basic, one of the basic facts that makes an ideal transformer ideal. As I said, an ideal transformer is just a magnetically coupled coil. So you have two coils that are magnetically coupled, and we use the same dot convention, right? But then the first thing is, the first fact is that the magnetic material is ideal enough such that K approaches unity. The coupling becomes perfect, right? So that's the first basic major property of an ideal transformer. If you take two mutually coupled coils and improve the coupling, keep improving the coupling to where K approaches unity, that's one way to, that's you're on the path to create an ideal transformer. There is another thing though. The other thing is that for an ideal transformer to be desirable too, another important property is that if one side of the transformer is open, let's say V2 is open, and we have connection to the grid, let's say, or some power supply on the other side, right? If one side is open and we connect the other side, we want the current flowing. So the current flowing here, I2 is 0, definitely, right? Because it's open. But we want I1 to approach 0 too. We don't want the transformer, if it's not connected on both sides, to draw a lot of current, right? The property that allows us, that lets I1 approach 0 is that L1 and L2 need to approach infinity, right? So those are the two basic properties of an ideal transformer. K approaches unity, L1, L2 approach infinity. The closer we are to those two ideals, the more ideal a transformer becomes, right? So essentially, when it is unloaded or not connected from one side, it will not draw any current. And if it's connected, the coupling will be unity. Okay. So we want to analyze the ideal transformer and understand its characteristics. And it's easier in this case to forget about the coupling and the inductances. It's easier in this case just to start from the physics. So we have the coil. Right? Start from the physics and to know that the coupling is perfect. Right? So we know that those two things happen and cause the coupling to be perfect, right? So that means that the flux going from out of coil 1 is the same, exact same flux that goes into coil 2. So this is I1 of t, this is, let's say, I2 of t going in, this is the dot, and this is in 1, number of turns on coil 1 and number of turns of coil 2. Right? Because the coupling is perfect and the flux is the same, we know that V1 equals N1 d phi by dt. N1 phi is the flux linkage, of course, and V2 is N2 d phi by dt. This only happens in an ideal transformer. Right? Typically, phi is not equal between the two coils unless you have an ideal transformer. If you divide equation 1 over equation 2, I get the first formula for an ideal transformer, which is V1 over V2 equals N1 over N2. So the voltage ratios are just the turns ratios. That's it. Nothing more. I mean, it's that simple. Notice it's simplified. Making the transformer ideal simplifies things rather than making things more complicated, of course. Right? This is very useful, of course. Having a device that can do this is very useful. Why? Because you know, let's say, let me give you like a bit of background. Perhaps you know this already, but if you have some voltage source, right? Like you have a generator, let's say, I don't know, 120 volts RMS, and you have a load, and there's a transmission line. The transmission line, let me model it as a resistor, make things simple. So I have a transmission line from generator to load. Let's say the load is a bulb, light bulb or something, right? So this load is a light bulb, right? So what happens is that, yeah, you can deliver the power to the load, but the current passing to the load is passing through those resistors. So your I square R losses represent energy that is lost in transmission, energy that is not doing useful work, that is not reaching the load and doing useful work at the load. It's like an energy tax that you have to pay just to transmit the energy. Because of the nature of the losses for transmission lines being purely ohmic, meaning they depend on the current, so the P loss is proportional to I square R, right? It would be useful if we can find a way to reduce the current. And it turns out that the ideal transformer is just the kind of device that allows you to reduce the current. So it takes the current here, it reduces it, and it increases the voltage. So the power is the same. It reduces the current, increases the voltage. And because it reduces the current, it substantially reduces the transmission losses. That's why, right? And then you go on the transmission line, and then at the end you have a step-down transformer that takes the voltage and pulls it back down, and then increases the current again. That's why in power transmission, the utility might be generating the voltage at a certain voltage, right? They have what's called step-up transformers before they send it over to the transmission line. So they can raise the voltage, I don't know, from maybe 1 kilovolt to like 12 kilovolt, and then they might have another transformer that raises the voltage again to even hundreds of kilovolts. Like I don't remember the figure, maybe 600 something kilovolts, right? High voltage, extremely high voltage transmission lines, and then those are transmitted for miles and miles and miles across the continent, hundreds of miles, and then at the end where the load exists, you step the voltage down, right? And then you step it down again until it reaches the 120 volts of your home, right? The technology that enables this is the transformer. Without the transformer, I mean, transformer is one of the most important inventions in the power systems industry. Without the transformer, this whole thing wouldn't have been doable 100 years ago. Okay? And this is one of the reasons why AC transmission won over DC transmission. Right? Because in AC transmission, you can do exactly this. The transformer exists for AC voltages and AC currents. It can do exactly this functionality for AC voltages and currents. There is no DC transformer. At least there was no DC transformer 100 years ago. There is a way to transform the voltage these days and raise it to a high level, but it's much more complicated. It's much more technologically advanced. It definitely was not available 100 years ago. Right? So if you've ever heard of HVDC, high voltage DC transmission, that's what I'm talking about. So it's in this technology, the people use switching devices to achieve something akin to the transformer. But the transformer is a much simpler device, much cheaper device, and it is the main reason that AC transmission won out over DC transmission. Okay, so having gone through the segue, let's go back to the analysis. So we said, hey, we established the first relationship, which is V1 over V2 equals N1 over N2. And this is for transformer that looks like this. This is I1, and this is I2, and this is V2, and this is V1. What about the relationship of the input current and the output current? Well, this we derived from Faraday's law. Here we have to use Ampere's law. And again, you don't have to remember this exactly. I'm just writing it for completeness. I'm not sure how much detailed physics you went through when you took physics 2. And I think you'll study this. Yeah, you will study this again when you take EM fields. But essentially, Ampere's law, when I write it down, it states the following. If you integrate the magnetic field intensity versus length, you get the I enclosed. So I have my core here and have my windings. If this integration is happening over a path, this path, right? If I integrate the field, the magnetic field over this path, the integration of this magnetic field over this path equals the total I enclosed. But what's the total I enclosed in this path? Well, the total I is I1 times the number of windings, right? If you look at this path here, let me zoom in. Here I have, within this loop, I have the current coming in n times, right? N1 times. So this X, imagine it to be the wire coming into the plane. So it's coming in 1 times, right? And then on the other side, the current coming into this plane is also coming in 2 times. So this is plus N2 I2, right? Now here comes the other basic property of the transformer that makes it an ideal transformer. The assumption is that the magnetic material has a very high permeability. When the permeability is very high, that makes the L approach infinity, right? So the permeability is incredibly high. That means that we don't need much H field H field is the magnetic field intensity. It generates the magnetic flux. The magnetic flux density is mu H. What having an ideal magnetic material or a very high permeability magnetic material means is that you don't need much H field to generate a flux density in the material. You don't need much H to generate B or phi. Ultimately, phi is just B times A, the cross-sectional area. Right? So this thing approaches, the left-hand side approaches 0. Right? And this gives us the second relationship, which is N1I1 plus N2I2 equals 0. Okay, and those simple relationships describe the input-output characteristics of the transformer. So transformer is typically designated like this. It's two coils with a core in between. So notice I'm drawing those two lines here, which represents the core, and I have the dot. And then this is I1, I2, V1, V2, and due to the tight coupling and due to the L1 and L2 and the high permeability of the magnetic material approaches infinity, the permeability of the magnetic material, and hence L1 and L2 approach infinity. Due to those two properties, V1 over V2 equals the relationship between the input and the output reduced to those two simple equations. Notice we don't have the di over dt anymore. We have this V1 over V2 equals N over N2, and N1 I1 plus N2 I2 equals 0. I could rewrite this, so it's easier to remember this in this form, but I could rewrite this as follows. I could say I1 over I2 equals minus N2 over N1. Right? I'm just rewriting this equation in this form. Just take N2I2 to the other side, it becomes minus N2I2, and then divide by I2, and then divide by N1. Okay, of course, this is using this convention. A more popular convention with transformers, with ideal transformers, is this convention where I1 is going into the dot. I have my core, and then I2 is going out of the dot. Right? So remember here, the convention is important. Using this sign convention where the currents are going into the dots, this is the relationship. Using this sign convention, all that is changed here is I2 is flipped. So I2 becomes negative I2, right? So we end up with V1 being the same, V1 over V2 equals N1 over N2. And here I have N1 I1, and I just flip the sign of I2. So I end up with minus N2 I2 equals 0, and I can rewrite this as N1 I1 equals, why do I write the 1 like a 2? Okay, equals N2 I2, so I1 equals N2 over N1. I take I2 to the other side, so I1 over I2 equals N2 over N1. So those two ways of expressing the VI relationships are valid, and the only difference is the sign convention. You should always be careful about what the sign convention is when you see a circuit, or when you draw a circuit, or when you try to solve a problem. Okay, let's examine the power. So this is the ideal transformer. What is the power in this situation? What is the power being what is the power that is being absorbed into the transformer at any moment in time? Well, let's take this basic equation in N1I1. Let's use this convention. So N1I1 plus N2I2 equals 0. Let's divide both sides by N2. So I end up with N1 over N2I1 plus I2 equals 0. What's N1 over N2? That's V2, right? So this is, V1 over V2, right? I can multiply now both sides by V2. So I end up with V1I1 plus V2I2. What's V1I1 though? That's the power going into port 1. What's V2I2? That's the power going into port 2. Right? So the total power going inside the transformer is always going to be 0. The transformer just transfers power from one side to the other side. It does not consume any power. It does not absorb any power, or does not give any power. It's just a mechanism for transferring power. The total power absorbed into the transformer is always going to be 0. This is like a very also another basic property of the transformer. Okay. Yeah. What else? I wanted to. Yeah, I'll talk about reflected impedance next time. So I think this is enough for today. All right. Thank you, guys. We'll continue this discussion next time.